Hey, this is Horner. We're going to look at 16.5. This is motion of a point charge in a uniform electric field. So the picture that you see here are a couple of metal plates, and they're both charged, so they're probably plugged into something to allow the electric field be generated between the two plates. So this is a three-dimensional view. This is a view from the side, and you'll notice that we have the positive plate on the right for this one and the negative plate on the left. And remember, charge always flows from positive to negative, so our electric field lines go from the right side to the left side. And you'll also notice that this field is uniform, where all these lines are exactly the same space apart from each other, and that's just a property of electric fields, is they should be uniform in this space. So remember, electric field is equal to charge divided by the permittivity of free space times the area. So if we knew the area of the plates, we know this value, and we know the charge, we can find that electric field. The force due to the electric field is equal to Q times the electric field. And then the acceleration is force over mass, or we can say it's that charge times electric field all divided by mass. So just a little bit of a review of some of the equations we've looked at. So the direction of the acceleration is either parallel for a positive charge or anti-parallel, which means it's just going the opposite direction for a negative charge. And to really see that, we need to do a problem. So this first one is called a cathode ray tube, so for 16.9, and this is used in some old televisions. Okay, so the flat screens don't do this. These are the old great big tube TVs. Computer monitors, the old ones, oscilloscopes, x-ray tubes, those type of things. So electrons basically come off a heated element or filament, and they go through a hole, and then they're accelerated by an electric field. So this has been really important for looking at imaging and things. They have an electron passing through a hole in the cathode. It's going at 1 times 10 to the 5th meters per second towards the anode. So one's positive and one is negative. The electric field is uniform between the anode and cathode, and it's got a magnitude of 1 times 10 to the 4th. So the first thing we want to do is find out what is the acceleration of the electron, and then the next thing is to, if the anode and cathode are separated by 2 centimeters, they want us to find out what the final velocity of the electron is. So this is a good picture, kind of a see-through picture of a CRT. Here's that heated filament. This is what we call the electron gun part, because it's producing electrons, or it's shedding electrons off that heated filament, passes through this hole in the cathode. Remember, electrons are negative, the cathode's negative, so they go screaming away from it towards the anode through another hole. And then there are plates, plates that are in both the vertical and the horizontal plane, and those help direct the beam to hit this screen, and that's what gives you a picture. If we look at just this part to the side, you'll see the cathode, the negative, and then the positive field, and you'll notice the field lines are going right to left, but the electron's going to go in the opposite direction, since opposites attract and the same things will repel. So that's kind of what you'll see. In order to do this problem, we've got a few things we have to know. The first one is the initial speed of the electrons, the separation between the plates, and the magnetic field magnitude. We'd have to look up that electron mass and the charge. Remember, that's in 16.1, and then we're going to find the acceleration in that final velocity. So let's go ahead and get started doing that. And to do that, the first thing we want to do is we've got to say that the force due to gravity should be equal to mass times gravity. So let's find the force due to gravity on that electron. The mass of the electron is about 9.1 times 10 to the negative 31st kilograms, and we'll multiply that times the value for gravity, which is about 9.8, and we should end up with somewhere around 8.9 times 10 to the negative 30th newtons. And remember, that's really small because we're talking about a very small item, the electron is just extremely small. The force due to electricity, let's make that a capital E, is equal to the charge on the electron times that electric field. And so the charge on an electron is 1.6 times 10 to the negative 19th, and we can multiply that times that electric field, which is 1.0 times 10 to the 4th, and that is a Newton per Coulomb. And so this is equal to 1.6 times 10 to the negative 15th newtons. So at this point we can find the acceleration. The acceleration, remember, is equal to the force over the mass, and here we've got the mass of an electron, and we said that that force is equal to the charge on the electron times that electric field, all divided by the mass of the electron. And so this is equal to 1.6 times 10 to the negative 19th times 1 times 10 to the 4th. So those are the charge on the particle, and then the electric field divided by the mass, which is 9.1 times 10 to the negative 31st kilograms. And so here we end up with an acceleration of about 1.8 times 10 to the 15th meters per second squared. Since the charge on that electron is negative, the direction of the acceleration is opposite to the electric field. So in that figure it'd be going to the right, going left to right. So that's finding that acceleration of that particle as it moves through. For letter B, the thing that they'd like for us to do is try to find the speed of the particle. So if you remember your kinematics equations, we can say Vf squared, so this is part B, is equal to the original speed squared plus 2 times the acceleration, which we just found, times the distance. And so this is really equal to the square root, and our velocity was 1 times 10 to the 5th. And so we will square that plus, and then we have 2 times our acceleration is 1.76 times 10 to the 15th meters per second squared, and then our separation was 0.02 meters. So when we're done, we get 8.4 times 10 to the 6th meters per second, and that is going to the right. So that is how to work example number 16.9. Let's go back to the notes that we were taking a look at. We've got another problem we need to do. This one, we have an electron is projected horizontally into a uniform electric field. That electric field, you'll notice, is pointing down between two parallel plates. The plates are 2 centimeters apart, and they have a length of about 4 centimeters. The original speed of that electron is 8 times 10 to the 6th, and as it enters the region between the two plates, it's midway between the two, and as it leaves, the electron just misses this plate here. They want us to try to figure out what the magnitude electric field is. So one of the things that I would do is remember that the top part of this plate, the top plate is positive, the bottom plate is negative, and that's because we know that charge flows from the positive to the negative plate. So to find the magnitude of this electric field, there's a few things that we need to do. And so let's go ahead and go on to the next slide. We know that that change in position is about 4 centimeters. We know that in the x direction, and the y direction is about 1. So remember, the entire thing, we'll back up here for a second, was 2 centimeters, but we started in the middle. And so the change in y position is about 1 centimeter because we just barely missed that plate. And the velocity of electron as it's moving into the field is about 8 times 10 to the 6th. So first thing we probably need to do is let's figure out how long it takes for it to travel. So we know velocity is equal to the change in position over the change in time. And so our time that it takes is equal to the change in position over our velocity. Change in position, we need to do this in meters, so this is going to be 0.04 meters divided by the speed, which was 8 times 10 to the 6th meters per second. We divide the two, the meters cross off, and the seconds comes up top. So we end up with 5 times 10 to the negative 9th seconds. So this happens very quickly as it goes through. Whenever anything is accelerating, we can use the equation, the change in the y position is equal to, now it doesn't have any velocity in the up and down direction, so usually we have v-o-y-t plus 1/2 the acceleration in the y times the change in time squared, but this is 0 because there's no acceleration, there's no velocity in the y. So let's find the acceleration in the y direction. That's equal to 2 times the change in the y position all over the change in time that we've already figured out squared. And so this is equal to 2 times 1 times 10 to the negative second, so that would be that 1 centimeter, and just another way to write it, all divided by our time, which we said was 5 times 10 to the negative 9th seconds, and we've got to square that. At this point, we should have a acceleration of 8 times 10 to the 14th meters per second squared, so really huge acceleration. We want to find out what that electric field strength is, and if you remember, we said that the force, and here we're going to do this in the y direction, is equal to the charge times the electric field in the y direction, and force is also equal to the mass of electron times the acceleration of that electron in the y direction. Using what we have right here, we can rearrange the equation. I'm going to change colors and go to blue here since we're finding the actual final answer here. And so we're going to rearrange the equation. This is the electric field is equal to, now we're going to divide both sides by Q. So we end up with the mass of the electron times the acceleration in the y, all divided by the charge. And oops, that's a G, and I want a Q there. So we'll back it up, divided by the charge. So this is equal to 9.1 times 10 to the negative 31st. We're going to multiply that times the acceleration that we just came up with, which is 8 times 10 to the 14th. And we're going to divide that by the charge. And remember, this is an electron, so our charge is negative. So it'd be negative 1.6 times 10 to the negative 19th coulombs. When we're done, we end up with negative 4.55 times 10 to the third, and then our unit here is a Newton per coulomb. And so since there's no x component at all, we're just worried about the y. Then the field has a magnitude of 4.55 times 10 to the third newtons per coulomb. And we are done. So that would be the electric field strength for that situation. The next thing we want to do here is do this quick check. It says a proton is moving to the right in a vertical electric field. A very short time later, the proton's velocity is what? So what I always like to do on these is draw the two plates. So there's one plate, this is the other plate, and remember we always go away from the positive plate and we always go towards the negative plate with our electric field lines. So a little bit later after this, so this is not the direction it's moving, this is its velocity. It's actually going to move a little bit differently. So we know that the opposites will attract, so the proton is attracted to the top side, it's repelled from the bottom. So we've got to think about which one of these this is going to be. And this one should be an acceleration that is going, really the change in acceleration is going to go straight up. But that means that our new velocity after a very short amount of time is going to be up and to the right. It's not going to be a lot up and to the right yet. It's not going to be totally straight up. Definitely not going to be to the right or down. So it's going to be letter C, and this is our little bit of vertical acceleration that we start to have. For the next one, this is 20.30 quick check. It says which electric field is responsible for the proton's trajectory. So notice that this thing is moving in a curve, okay? And so we've got to figure out which one of these is producing that curve. If we draw, let's go ahead and draw two plates. Let's put one here and one here for letter C. And this would be the positive side, and this would be the negative side. And you'll notice that if I had a proton coming in at this angle, if it was right here, okay, and it's coming in, it's going to go up until it stops in the x direction, then it's going to come back the other way. So it looks like C is going to be our best answer, and it is. This electric field is a little different. It looks like we've got a couple plates here. This one does not exist. This one wouldn't exist. So it's either got to be C or D. Those are the two that we really want to choose from. And that is the end of section 16.5.